All right, so let's look at this impulse lab. Okay, so we took some theory that the sum of the forces is equal to ma, and we looked at what would this look like if there was a single force causing the acceleration. So when the car hit the bumper, there was a force on the cart due to the bumper that caused it to change velocity. It was going towards the bumper, and then it bounced off going away from the bumper, so there was a change in velocity. So then that gave us F is equal to m, but A is really defined as the change in velocity over change in time, or dv dt for those of you that are in calculus. So that would be like delta V over delta T. And then we multiplied the delta T on both sides and got this expression. And so then your job was to hopefully see that when you take the force time information with the force sensor and the velocity time information with the motion detector, that you could get equivalent values for this equation. So use the force sensor for the left side of the equation, used the motion detector for the right side of the equation. Did many of you get an area that was close or equal to the change, the m times delta v? Got some relatively close numbers? Close enough for government work? Just kidding. All right, so did your force graph look like this, though? Was that surprising that it was negative compared to what we looked at before? It's based on the direction. And then, but your velocity graph then looked like this. And hopefully you saw that it started with a positive velocity, had a maximum negative slope, and then like that. So we had a change in velocity. And hopefully that this point right here matched the time when this one crossed through the time axis there, because this would have been our greatest acceleration, the greatest slope right there, and this would have been our greatest force, which would be our greatest acceleration. And the area under the curve, also known as the integral, you found with the calculator. So you found this area. You use the approximate mass of the cart, and some of the carts are 500 grams. Some of them are closer to like 516. So you may have a slightly different mass times velocity number based on the fact that you didn't have the mass of your cart, you had the average mass of the carts. And then, so that should have been equal to m times delta v. And I hope that you got numbers that were relatively similar. So this area thing is called the impulse. Now, if you think about it, impulse is this weird thing. It's the product. It's this multiplication of a force times the time that force is acting. And just in very simple terms, an impulse is just a little poke. Okay? It can be for a longer amount of time. Have you ever seen a rocket launch? Is there force from the gases leaving the rocket pushing down on the earth, and that acts for a particular amount of time? So as long as there's a force acting on an object, there is an impulse. But an impulse can be as simple as just a little boop, little poke. So when you pushed the cart, you actually gave it an impulse. Okay? Now, that impulse is equal to this mass times the change in velocity, which would be mv minus v initial, which is the same thing as mv minus mv initial. And this product of mass times velocity has its own special meaning. Almost. It looks a lot like kinetic energy, because what was kinetic energy? 1/2 mv squared. Ooh, so it looks like it's kind of embedded in kinetic energy. But it is momentum. So you probably hear or have heard the word momentum more than you've heard impulse. That's my guess. As I was watching football over the break and all the bowl games, I heard momentum several times. If I listen to NPR and I listen to any of the candidate for president, the presidential race information, a lot of times the word momentum will be used. So in sports, a lot of times we'll say, "Oh, this team is gonna take the momentum from this win, and that will blah blah blah," right? This team has gained momentum this season. In basketball, a lot of times a coach will call a timeout because the other team is scoring and has made lots of baskets, and it's to break their momentum. Football, a lot of times right before a field goal, they'll call a timeout, and that's a lot of times to kind of break the momentum. And those aren't wrong ways to think of momentum, because no matter what, you're thinking about something and this quality about it moving. So physically, in physics terms, momentum is truly the amount of mass times its velocity. And so an impulse causes a change in momentum. So this m times v is momentum. And we ran out of letters in the alphabet, so momentum, the symbol is a lowercase p. So p is equal to m times v. If you're looking for initial momentum, you would just use the initial velocity. If you want final momentum, you would use a final velocity. So the mass is in kilograms, and the velocity is in meters per second. So what is the unit for momentum? What did we multiply? You take kilograms and you multiply it by meters per second. And a Newton times a second should be equal to a kilogram meter per second. We can show that because a Newton is force, and force is mass times acceleration. So that would be kilogram meter per second squared times seconds. Did I make a good little proof there? My seconds divided by seconds squared give me just 1/4 seconds. So that's why, yay, my units check out. That impulse and momentum have equivalent units. Therefore, they are equivalent. So let's look at the long sentence here. Impulse is and I'm going to write the average force times the change in time. And I'm going to explain that in just a second, why I made it force average, is equal to m times delta v, which would be equal to m times v minus m times v initial, which would be p minus p naught, which would be equal to delta p, which is change of momentum. Let's look at why I put that little subscript average. I'm going to go back up here. And this was like your force graph. Now, if you needed to find the area under this thing and you didn't have the exact force values, or it was this funny shape or something like that, if you had the average force, so I'm going to use another color here. So maybe you have the average force. Well, the average force would kind of be like in the middle, right? And if you took the average force and multiplied it times the time, and it looks better if you do it, if you model it as a triangle. So if we were to model this as a triangle instead of like a upside down parabola or the bottom of the sine type curve, do you see where the area here is about equivalent to this area there? And that this area here is about equivalent to the area there, which is why a good estimate of the impulse, okay, would be the average force times the change in time. Because when your force is changing, it's not the same all the time, but you could find an average, which gets you closer to the impulse, at least if you were estimating, okay? So that's why I put the average subscript in there. Okay, so the big picture, the big idea is that impulse causes a change in momentum. And likewise, a change in momentum is caused by an impulse. So remember we looked at work and energy, and they're different words, and they're slightly different physical things when you think about force times time, force times distance, and then like this kinetic energy business. But work caused a change in energy. An object has energy because work was done on it. So impulse causes a change in momentum. Or you can think of it as a change in momentum must have been caused by an impulse. There has to be a force to cause an acceleration, which would cause the velocity to change. Therefore, momentum changed. And if there's a momentum change, that means that there had to be an impulse. So if you're looking at something and it speeds up suddenly, there was an impulse from something. Because anytime a momentum change occurs, there must be an impulse that caused that. There must have been a boom. So when you're running along and suddenly you start sprinting, you start pushing more. So you are applying an impulse to your system of running. Okay?